Hello. At the end of last semester, we used tables to help us sort out equilibrium problems, and it seemed like we didn't fully understand how to use those tables. So I want to go through that. I'm going to start by generically talking about it, and then we're going to look at how this plays out for specific examples. All right. So when we have multiple forces, usually three, acting on a point, we might have something like this where, force A is over here, force B is up there, and then force C is over here, okay? And if those things, if the point that they're attached to, if these all represent forces, if this point isn't moving anywhere, we know that A plus B plus C must equal 0, all right? So we just talked about, we could express A as in component form AX comma AY, and we could do the same thing for B and C. But it's also often easiest if we put those in a table. So if I were to put over here like a little table of force versus the X component versus the Y component, then I could, in my table, A, B, I'll put a double line right here. Okay, and this will be A, B, and C, and this will be the total. So I'll call this, the sum of the forces. All right. Now, generically, right now, we don't know anything about A, B, or C. So when you start the table, just sort of assume that everything is an unknown. AX, AY, BX, BY, CX, and CY. All of those are unknown. So we're going to leave them as AX, BX, CX, AY, BY, CY. But we do know that those total to 0. Now, what I'm going to do is go through a series of examples where we can then start plugging in information to begin to solve the problem. Okay. So the first example I want to look at is one like this, where we know that A is pulling down. Let's just say we'll work with pounds this time. Let's say that that's a 20-pound force and it's straight down, right? And then we have a vector B. And let's say that that's 10 pounds and it's at an angle. You can see it's kind of vertically upward. Let's make that angle, it's 20 degrees up from horizontal. Okay, and then there's a vector C. So this was A, this was vector B, and there's a vector C, but we don't know, it's over here somewhere, but we don't know the magnitude of it or the direction. And let's see how that would play out in the table that we just had. Okay, so let me make my table. 3 columns, so plenty of room here and there. So here's the force. Here's the X component. Here's the Y component. Okay. Here's A line there. B, put in a line. C, put in a line. And then we have the sum of the forces. All right. I can erase these. Okay, a little too much room there, and we can start filling things in. Now we know that if this isn't moving, the sum of the forces again is 0. Okay, now for A, we can fill in the X and Y components. It is not at all in the X direction, and it's clearly -20 in the Y direction. We're going to assume that upward is positive, so that's a -20 because it is downward, right? Now for B, we can fill in information. Okay, so we could just write, BX, BY, and CX and CY, because we don't have all of the information for those. But we can replace some of this because we know for B that it is at an angle of 20 degrees. So obviously we want to use that information. Now for C, on the other hand, we know nothing about it. So This is what we should leave for vector C because we know nothing about C. So we will leave those components as just Cx and Cy. You would know absolutely nothing about them. But for Bx and By, they can be replaced because we know there's that 20-degree angle. Okay. Now we know we need to think about components and triangles here. There is a triangle for vector B that looks like that. Okay, and the adjacent side would be Bx and the vertical side would be By. So we know that for Bx, we could replace it by 10. Oops, I should put a negative in front of that because it is to the left. So I can replace it with a negative 10 times, and since it's adjacent to the 20-degree angle, I would say cosine of 20 degrees. In the vertical direction, the y direction, it is upward. So even though we could leave that as by, but we have information about the angle. So we can say that this is 10 times the sine of 20 degrees. And by the way, those are numbers. Okay, we know we can, I'm going to actually compute them right now. 10 times cosine of 20 degrees gives me a negative 9.40. And 10 sine 20, 10 sine 20 gives me a 3.42. So we actually have a number for Bx and By because we know the angle and we know the size of the force, right? So now if we look at each column, we can see that in the X column, the only thing we don't know is Cx, and in the Y column, the only thing we don't know is Cy. And I probably should put a double line here because that's where we're totaling A, B, and C. And so the double line kind of corresponds to an equal sign. So if I look at the X column, in the X direction, I can write that 0 minus 9.40 plus Cx should equal 0. And if I look at the Y column, in the Y direction, I should be able to say, I just add up the A, B, and C, negative 20 plus 3.42 plus Cy. It's also equal to 0. So this tells me that the unknown force has an X component of 9.40 pounds. It needs to pull to the right to counterbalance B pulling to the left. And then Cy, let me just make sure I get this right. This will be 20 minus 3.42. So that's 16.58, I believe. Okay, so the Y component of C needs to be 16.58. Okay, since B is pulling upward a little bit with a force of 3.42 pounds, C doesn't have to pull up quite as much as the 20-pound downward force in order to get this to work. Okay, now if we need to find the magnitude of C, so we now know that C is 9.40 comma 16.58. Notice both X and Y are positive, so this is a quadrant 1 kind of answer. If we need the magnitude of the force, we can just say that the magnitude of C is the square root of 9.40 squared plus 16.58 squared. And the direction, since it's quadrant 1, we don't need to worry about fixing it, is simply the inverse tangent of 16.58 over 9.40. I'm not going to take the time right now to compute those. Those are simple calculations at this point. Okay, so when you don't know anything about a force, leave it in complete component form. Okay, so C was not known at all, so we just left it as Cx and Cy. And B, because we knew how the magnitude and direction of the force, we actually wanted to compute the size of each of the components and put them right there in the table, and then it was very easy to add up. Okay, so that's one example. Okay. The second example is where you know all of the directions, but you don't know two of the forces. Okay. And then we're going to do a variation of that. So let's say that A is still 20 pounds downward. B is unknown in size, but we know its direction exactly. Okay. In fact, let me put that in as a dashed vector because we don't know its magnitude. We know exactly what direction it's in. It's in that direction, but we don't know how big it is. All right. And then vector C, we're going to put that. We don't know how big it is, but we do know that it's at exactly a 30-degree angle. Okay. So now we have angles, we have directions for everything, but two of the forces are unknown. So let's go ahead and put this into a force table. So force, we have A, B, C, and then we can put our double line in for the sum of the forces. And I'll subdivide this down. Those are going to total to 0. And here's the X and here's the Y component. All right. And just like before, let's put a couple lines here. We know that just like before, this is 0 and negative 20. Right. Now B, we don't know both components, but we do know one of them. We don't know what B in the X direction will be, but we do know that it's not at all in the Y direction. So I can put a 0 there, which means that 100% of B is left in the X direction, but it's pointing to the left. So I'll call that negative B. So whatever the size of B is, if that were a 10-pound force, it would be negative 10 in the X direction. It would be 10 pounds to the left. We don't know how big it is, but we do know it's to the left, so I'll put a negative there. Okay, so you can see we have one unknown for B. It's the component in the X direction, but we do know that it's 0 in the Y direction, right? Now C, we don't know, we know that it's at 30 degrees, but we don't know, how big it is. So you might be tempted to just say, oh, this is CX and CY, all right? You could do that. We could solve for CY in the Y column because we know everything except for CY. But we also, we haven't used the fact that we have the 30-degree angle yet. Okay, so we want to bring the 30-degree angle into play before we try to solve anything. Okay, so since we know that that is a 30-degree angle, while we don't know what C is, we can say that the X component is C times the cosine of 30 degrees, and the Y component is C times the sine of 30 degrees. Okay? Then you can see the only thing we don't know in the Y column is the value of C. So we aren't just finding CY by using the Y column, we can actually solve for C itself. So if we start with the Y column, we can say that negative 20 plus 0 plus C times the sine of 30 degrees must be 0. So that means that C times the sine of 30 is positive 20. Add 20 to both sides. Hopefully you remember that sine of 30 is 1/2. So 1/2 of C is 20. Okay, don't divide both sides by 2, multiply both sides by 2. So C must be 40 pounds. Okay. So we just solved for C using the Y column. Now that we know that, we can go to the X column. And we know that using the X column, 0 minus B plus C times cosine of 30 degrees must be 0. So 0 minus B plus, we now know that C is 40. 40 cosine of 30 degrees is equal to 0. Hopefully I'm going to do this in 2 steps. I'm going to multiply by -1 and move the 40 cosine 30 to the other side. So B must equal 40 times cosine 30. So just quickly on my calculator, 40 cosine 30 is 34.64 pounds. Okay, so we've now solved for what the other two forces would be. Okay, so we knew the directions of both, and this problem was a little easier because B didn't have a y component. Now let's change the problem slightly where B will have a y component. So it'll be almost the same problem, but this time B will have a y component, and the algebra will end up being a little bit trickier. So we're going to have A being 20 pounds downward. All right, and this time B is going to be this way. Whoops, and let me make it dashed because we don't know what its magnitude is. So B is going in this direction here. And I'm going to say that that is relative to the horizontal. That is 20 degrees above the horizontal. So B is going at 20 degrees above the horizontal, but I don't know how big it is. C, like the last example, is going to be 30 degrees above the horizontal, and I don't know how big it is. Okay, so I don't know the magnitude of either B and C, but I do know all of the directions. Okay, since I know the directions, I want to work those into the table. Okay, so here's the table. Force A, B, C, double line, divided into the X and Y parts. Okay, so A, once again, 0, -20. We know that the totals, whoops, I should write some of the forces, will be 0. Okay, and nothing has changed with C. So just like in the last case, we don't want to write CX and CY because we do know there's a 30-degree angle. So we want to get the 30 degrees to show up in the math of this. So we will say that this is, in the X direction, C times cosine of 30 degrees. And in the Y direction, this is C times the sine of 30 degrees. Likewise, we do the same thing for B. We know this is a 20-degree angle. So we want to work this in. Now the X component will be to the left, so it's negative B times cosine 20. Quick aside, if that's 20, this is 160 degrees. So if you wanted to, you could have used B times cosine of 160 degrees, but that is the same as the negative of B times the cosine of 20 degrees. So just that's a quick aside there. It's because the cosine of 20 degrees is a reference angle for 160 degrees, but 160 is second quadrant, so the values will be opposites of one another. Okay, and then we have over here this, it's upward, B is upward, so this would be B sine of 20 degrees. You could use sine of 160, but it turns out that because sine of 20 and sine of 160 are the same, 20 degrees is the reference angle, but it will, their first and second quadrant signs are both positive, so those will be equal to each other. So I tend to like to use the reference angles to make the math a little bit easier. Okay, so let me actually clear out a little bit of space, so I'm going to get rid of these aside items and continue onward. So now we need to add this up, and this is mathematically a bit trickier. Okay, so I have two unknowns in both columns. Notice B and C are unknown in both the X and the Y column. So I can't use one column to solve, whereas in the previous example, C was the only unknown in the Y column, whereas the X column had B and C as unknown. So we started with the Y column where there was one unknown. Okay, moving along. Since there's no reason to favor x over y except alphabetical order, we'll start with the x equation. I'll leave out the 0 and say negative b cosine of 20 plus c times the cosine of 30 degrees must equal 0. And it's good to work when you're going to have to do simultaneous solutions. It's good to put them next to each other like this. So negative 20 plus b times the sine of 20 degrees plus c times the sine of 30 degrees is equal to 0. And that can be rearranged to make everything positive. B times sine of 20 plus c times sine of 30 degrees is equal to 20. Okay. Now, hopefully you can see that the, if I do the same thing for the x equation, I can say c times cosine of 30 degrees, make everything positive by bringing this to the other side. In other words, adding b cosine of 20 to both sides. We can see that the x equations are simpler than the y equation. So the best thing to do is solve for either c or b in the x equation. I'll solve for c. Okay, and then we're going to substitute that over, okay? If it makes it easier, what you could do at this point is realize that cosine of 20 divided by cosine of 30 is a number. So cosine of 20 divided by cosine of 30, I'm just entering this into my calculator quickly, is the number 1.085 out to the thousandths place. I would certainly go to the thousandths place if you're going to approximate. Can go right there. Okay, and while we're approximating, let's go ahead and make approximations for all of these things. Okay, sine of 20 can be approximated. So sine of 20 is to the thousandth place 0.342 times b plus sine of 30 is exactly 1/2. So I'll put 0.500 times c must equal 20. Now, if we substitute, we can eliminate c. So let me go ahead and actually, let me stick with this for now. And 0.342 times b plus 0.500 times c. What can we put in for c? We can put in 1.085 times b is 20. So that's what we're subbing in. Now, if we multiply these together, and we'll get 0.342 times b plus 0.5 times 1.085 is 0.54 to the thousandths place. That would be a 3 times b is equal to 20. So we can add these up. We have two terms that both are in terms of b. So we can add these numbers together. So plus 0.342. And we end up with 0.8845 times b is 20. Notice how I put the decimal within parentheses. That's not a bad idea to do, just so that you can separate it out and it doesn't get muddled with the number. So divided by 0.8845 is, whoops, b is 22.61. I think we have pounds here. Okay. Now that we've solved for b, we can sub back and solve for c. So c is simply that answer times 1.085. And we end up with c being 24.53 pounds. Okay, so those are my answers for the magnitudes of B and C. Now, real quickly, let's see if those answers make sense. So let's say 22.6 and 24.5. 22.6, I think that was the answer. And 24.5, if I round those. You can see that the upward forces are larger than 20 pounds, but their upward components will only total 20 pounds, okay? So they will balance out what A is doing vertically downward. And then if you were to look at, since B is a slightly smaller angle, it needs to be pulling a little bit harder. C is pulling, ooh, I'm sorry, I reversed my answers, okay? This is 22.6 and this is 24.5. Since B is more directly pulling to the left, it doesn't have to be quite as big as C in order to balance out C in the left and right directions, okay? So those answers do make sense physically if you think your way through the problem, and that's how you do these problems. All right. So when you have information like an angle, you want to work it into the table. Occasionally, you end up with simultaneous equations that need to be solved. And that will happen, I believe, on the last problem of your homework. So you'll want to pay attention to how that was done.